We are going to learn how to determine solutions from a reduced row echelon form matrix. To do this, we are going to look at the 3 examples on the back of the 11.1 note guide. Just a reminder, these 3 examples are not yet in reduced row echelon form. In order to get them into reduced row echelon form, we either need to solve them with using a graphing calculator or Wolfram Alpha. Just a reminder, in Wolfram Alpha, we use the RREF command, which stands for reduced row echelon form. We always open up a bracket, it's like this curly bracket, to signify the start of a matrix, and then we open up a new bracket for each row. Notice that for each row, I enter the 4 digits in this case, 1, 2, 3, 4, with commas in between, and then I end the row with a curly bracket. In between the curly brackets, I use commas. Here you can see row 2, again with a comma, and then row 3. Finally, close your matrix with that last curly bracket. Once you hit compute, it will actually spit out the reduced row echelon form matrix. In fact, this is what you should get. Definitely practice doing this so that you know how to do so. Now, what does this matrix actually tell us? Well, let's look at it. What does this bottom row represent? Basically, it is saying 0x plus 0y plus 0z equals 1. Well, what happens if we know that 0 equals 1? That never is going to happen. It's not going to be true. So therefore, this particular matrix and system that it represents would have no solution. In fact, as we discussed in class, this means that the system would be inconsistent. Remember, with inconsistent systems, that's all you need to say. You don't need to do anything in terms of solving because there is no solution. Let's go ahead and move on to example 2. For example 2, we start with this matrix as shown here. Again, if I insert this into my Wolfram Alpha with the RREF command, if you need help, again, go back to the first example on how to enter it in, you should end up actually getting the reduced row echelon form matrix that looks like this. So what does this matrix tell us in terms of the situation? Well, this time we now have 0x plus 0y plus 1z equals negative 2. Or, in other words, we have that 1z equals negative 2. We also can see from this second row that 1y, or y, is equal to 3. And lastly, from that first row, I can see that 1x is equal to 10. This is a solved matrix because it's in reduced row echelon form, and we can now write our solution as an ordered triplet. In fact, in alphabetical order, like we usually do, it would be our x coordinate, which is 10, followed by our y coordinate, which is 3, and then lastly our z coordinate, which is negative 2. Moving on to our last example, example 3, we have this matrix here. Again, I'm going to use the RREF command on Wolfram Alpha to get this matrix in the reduced row echelon form. This one looks a little bit different than all the ones we've seen before because look at our bottom row here. We have 0x plus 0y plus 0z is equal to 0. Technically, this bottom row is saying that 0 equals 0, which is always going to be true. There is nothing that you can plug in that would make that not true. Therefore, this is going to be a dependent system. Remember, this means that there are infinitely many solutions. Just as discussed in class, when we have a dependent system, we want to set one of our variables, typically the third variable, equal to any real number. Again, we can introduce a parameter of t, or you can technically let z equal any real number that you'd like, because z is our third variable. For this example, let's go ahead and practice introducing that parameter t. So just like discussed in class, when we have a dependent system, we want to let that third variable, or in this case z, represent any real number. Again, we can introduce a parameter. We typically use the letter t to represent this. Otherwise, you can technically also say that z is just any real number. I'm going to go ahead and introduce that parameter just so that we can practice seeing what that looks like. So we're going to let z equal t, which is any real number. Once we have that, we're going to go ahead and go to this second row there. Again, that second row technically is saying that 1y plus 5z, which remember that z in this case is equal to t, so 5t is equal to 3. I can easily solve for y then in terms of t, or my parameter. So in this case, it'd be y minus 5t. Lastly, I need to solve for x in terms of t as well. So let's go ahead and go up to our top row. This top row is telling us that 1x plus 3, again, just a reminder that z is equivalent to t in this case, is equal to 2. Just like with y, we can solve for x then in terms of this parameter t. So x is equal to 2 minus 3t. Now that we've solved for both x and y in terms of z, or our parameter t, we can go ahead and write this as an ordered triplet. We know that x is 2 minus 3t. We know that y is 3 minus 5t. And then lastly, we know that z is just equivalent to t, which is any real number. That would be my ordered triplet for this dependent system.